Again, root locus diagram for the given control system is shown in the following figure. This is the number of poles and zeros are marked here. This one is poles located at 0, poles located at -1, poles located at -5, and the zeros are located. One is at -2, next one is plus j root 5, second one is minus j root 5, and the breakaway point is minus 0.473. So the point is from -2 is the breakaway point, break-even point. So the lines is now here. The breakaway point is now this point, that is 0.473. For this point, this is the breakaway point, and this is the angle of asymptotes originates at -2 points. So this is the line of -2 points. In this way, you can draw the root locus diagram of any control system and observe the movement of poles of the closed loop transfer functions. From the root locus diagrams, we can know the range of k values for different types of dampings. The effect of adding open loop poles and zeros on the root locus. The root locus can be shifted in S-plane by adding the open loop poles and open loop zeros. If we conclude a pole in the open loop transfer functions, then sum of root locus branches will move towards right half of the S-plane. Because of this, the damping ratio J decreases, which implies damped frequency omega d increases, and the time domain specifications like delay time Td, rise time Tr, and peak time Tp decreases, but it affects the system stability. If we include a zero in the open loop transfer functions, then some of the root locus branches will move towards left half of the S-plane. So it will increase the control system stability. In this case, the damping ratio J increases, which implies damped frequency omega d decreases, and the time domain specifications like delay time Td, rise time Tr, and peak time Tp increase. So based on the requirement, we can include or add the open loop poles and zeros to the transfer function. For example, the characteristic equation is given by SQ plus 3s square plus 2s plus k is equal to 0. So S is equal to, put S is equal to j omega. So this become minus j omega q minus 3 omega square plus 2 j omega plus k. So rearrange now k minus 3 omega square minus j omega common, that is omega square minus 2 is equal to 0. So omega square is equal to 2. So k is equal to 3 omega square, that is equal to 6. So that the k is equal to 6 point is here, and the poles are located at minus 1, and second one is plus j root 2, and next one is minus j into root 2. So this one is the pole -1 point, and the breakaway point is nothing but k is equal to 6 here. Why a circle characteristic equation is square plus s whole into 2 plus k plus 2k plus 1 is equal to 0. For k less than 4, for k greater than 4. For k less than 4, s1 and s2 minus 2 minus whole into 2 plus k plus or minus j square root of k whole into 4 minus k by 2. s1 2 is equal to minus of 2 plus k plus or minus square root of k whole into k minus 4 by 2. The change of origin s12 plus 2 is equal to minus of minus 2k plus minus 2 plus k plus or minus j square root of k whole into 4 minus k. So 4m is equal to k minus 2 rho square plus k whole into 4 minus k, that is equal to k square minus 4k plus 4 plus 4k minus k square. So m is equal to 1. Where k is equal to 4, then this is located at k is equal to 0. So now this is k is equal to 2, this is k is equal to 2, beta is equal to minus 3, and this is the 0 point is at minus 2 point. So the root locus is now following a particular circle. An effect of addition of poles and zeros on the root locus. So addition of poles to open loop transfer function has the effect of shifting the root locus to the right side in S-plane, that is lowering the relative stability and slowing down the settling of the response, increase of settling time. This one is the diagram. Here the diagram drawn between j omega versus sigma. This is the location of the poles. This is another two location of the poles, and this is the curve drawn between sigma versus j omega. Here three number of poles are here, and the breakaway points is there, and this is the angle of asymptotes and the draw between j and omega, sigma and j omega. Addition of zeros. Addition of zeros to the open loop transfer function has the effect of shifting the root locus to the left side in the S-plane, that is increasing the relative stability and speeding of the settling of the response, decrease of settling time. This is another root locus, and here also draw between sigma versus j omega. This is the location of the poles, and this one is the breakaway points, and this is the angle of asymptotes. Here also zeros location at this point. These are the number of poles, and here the breakaway points will be like this. And the third one, this is angle between sigma and j omega. Here the number of poles and zeros are indicated here. There are three number of poles and one number of zeros is there, and the breakaway points is here. Adding to right half of the plane 0 to the transfer function makes stable response slower and can make the response understood. Adding a left hand plane pole up to the transfer function makes the step response slower. Those dominant poles and zeros. First one is effect of a zero on the step response. Suppose that we modified the second order transfer functions given above by adding a 0. At s is equal to minus z for some time z, the modified transfer function is given by hz of s is equal to 1zs plus 1 omega 2ns square plus 2j omega n into s plus omega square into n. Note that the reason for writing the 0 terms as 1 zs plus 1 instead of s plus z is to maintain a DC gain of 1 and the transfer function, just so that we can compare it to the original transfer function. Hz of s is equal to omega square plus into ns square plus 2j omega n into s plus omega square n plus 1 zs w 2n square plus 2j omega n into s plus omega n square n is equal to hs plus 1 z s, where hs is the transfer function of the original system without the 0. Donate the Laplace transform of the step response for this system by y of zs is equal to h z of s 1s using the above decomposition of hzs. Y z of s is equal to hs plus 1 h z s hs 1s is equal to hs 1s plus 1 zs hs 1s is equal to ys plus 1 z sys. Nothing that the inverse Laplace transform of SYS is y. We obtain y z of t is equal to y of t plus 1 z y of t. Nothing that the inverse Laplace transforms of SYS is y. We obtain y z of t is equal to y of t plus 1 z y of t. Thus the step response of the second order system with a 0 at s is equal to minus z is given by the step response of the original system plus a scaled version of derivative of the step response of the original system. A sample plot of for z greater than 0, that is corresponding to the 0 being the OLHP, is shown in figure 1. Note that as z increases, that is at the 0 moves further into the left half of the plane, the term 1z becomes smaller and thus the contribution of the term y of t decreases, that is the step response of this system start to resemble the step response of the original system. From the above figure, the effect of LHP 0 is to increase the overshoot, decrease the peak time and decrease the rise time. The settling time is not affected too much. In other words, LHP 0 makes the step response faster. Now consider what happens if z is negative which corresponds to the 0 being in the ORHP. In this case, the derivative y of t is actually subtracted from y of t to produce yz of t. A sample plot is shown in figure 2. Note that the response can actually go in the opposite direction before rising to 1. This phenomenon is called undershoot. Step response of second order system with transfer function hzs is equal to 1zs plus 1 omega square n square plus 2j omega ns plus omega square n, where z is less than 0. 0 in the right half of the planes are called non-minimum phase. Minus the reason for this terminology will become clear later in the course. The effect of RHP 0 is to slow down the system and perhaps introduce overshoot. Figure 2. The step response of second order system with transfer function zs is equal to 1zs plus 1 omega square ns square plus 2j omega n into s plus omega square n, where z less than 0. 0 in the right half of the plane are called non-minimum phase. The reason for this terminology will become 0 later in the course. The effect of RHP 0 is to slow down the system and perhaps introduce overshoot.